Welcome friends. In this session, we introduce the concept of a function from one set into another. Without exaggeration, this is probably the single most important and universal notion that runs through all of mathematics. Functions. Suppose that to each element of a set A, we assign a unique element of a set B according to certain rule. Then the rule by which the assignments are made is called a function from A into B. Definition. Let A and B be two non-empty sets. A function from A to B is a rule which assigns to each element of A a unique element of B. A function is also called map or mapping or transformation. The set A is called the domain of the function and the set B is called the target set or codomain. Functions are ordinarily denoted by symbols. Let f denote a function from A into B. Then we write f is a function from A into B, which is read f is a function from A into B, or f takes A into B, or f maps A into B. Suppose f is a function from A into B and A belongs to A. Then f of A will denote the unique element of B which f assigns to A. This element f of A in B is called the image of A under F or the value of f at A. We also say that f sends or maps A into f of A. The set of all such image values is called the range or image of f, and it is denoted by range of f or image of f or f of A. That is, f of A is the set consisting of B belongs to B such that B is equal to f of A for some A belongs to A, which is the set consisting of f of A such that A belongs to A. Obviously, image of f is a subset of the target set B. Usually, a function is expressed by means of a mathematical formula. Consider the function which sends each real number into its square. We may describe this function by writing f of x is equal to x square, or x goes into x square, or y is equal to x square. In the first notation, x is called an argument or variable and the letter f denotes the function. In the second notation, the barred arrow is read goes into. In the last notation, x is called the independent variable and y is called the dependent variable, since the value of y will depend on the value of x. Furthermore, suppose a function is given by a formula in terms of a variable x. Then we assume, unless otherwise stated, that the domain of the function is the set of real numbers R or the largest subset of R for which the formula has meaning, and that the codomain is R. Suppose f is a function from A into B. If A dash is a subset of A, then f of A dash denotes the set of images of elements in A dash, and if B dash is a subset of B, then f inverse of B dash denotes the set of elements of A, each whose image belongs to B dash. That is, f of A dash is a set consisting of f of A such that A belongs to A dash, and f inverse of B dash is the set consisting of A belongs to A such that f of A belongs to B dash. We call f of A dash the image of A dash and f inverse of B dash the inverse image or pre-image of B dash. Example 1. Consider the function f of x is equal to x cube. That is, f assigns to each real number its cube. Then the image of 2 is 8, and so we may write f of 2 is equal to 8. Similarly, f of minus 3 is equal to minus 27 and f of 0 is equal to 0. Example 2. Let G assign to each country in the world its capital city. Here the domain of G is the set of all countries in the world and the codomain is the set of cities in the world. The image of France under G is Paris, that is, G of France is Paris. Similarly, G of India is New Delhi and G of England is London. Example 3. Find the domain D of each of the following real valued functions. F of x is 1 upon x minus 2, g of x is x square minus 3x minus 4, h of x is square root of 25 minus x square. Solution. F is not defined for x minus 2 is equal to 0 or x is equal to 2, hence D is the set of real numbers not containing 2. G is defined for every real number, hence D is the set of real numbers. H is not defined when 25 minus x square is negative, hence D is the closed interval minus 5, that is, the set consisting of x belongs to R such that minus 5 less than or equal to x less than or equal to 5. Example 4. Suppose A is the set consisting of A and B is the set consisting of 1, 2 and 3. Find the number of functions from A into B and from B into A. Solution. There are 3 choices, 1, 2 or 3 for the image of A, and similarly 3 choices for the image of B. Hence there are 3 times 3 is equal to 9 functions from A into B. There are 2 choices, A or B, for each of the 3 elements of B. Hence there are 2 times 2 times 2 is equal to 2 cube is equal to 8 functions from B into A. Example 5. Suppose A and B are finite sets with the cardinality of A elements and cardinality of B elements respectively. Show that there are cardinality of B raised to cardinality of A functions from A into B. Solution. There are cardinality of B choices for each of the cardinality of A elements of A. Hence there are cardinality of b raised to cardinality of a possible functions from a into b. The set of all functions from a into b is usually denoted by b raised to a. With this notation, by example 5, it is clear that if a and b are finite sets, then cardinality of b raised to a is cardinality of b raised to cardinality of a. Identity function. Consider any set A. Then there is a function from a into a which sends each element of a into itself. It is called the identity function on a, and it is usually denoted by 1 suffix a or I suffix a or simply 1. In other words, the identity function 1 suffix a from a to a is defined by 1 suffix a of a is equal to a for every a belongs to a. Functions as relations. Definition. Consider the function f from a to b. Then the graph of f is the set of ordered pairs ab such that a belongs to a and b is equal to f of a. Remark. Note that graph of f is a subset of the Cartesian product a cross b. Hence, every function f from a to b gives rise to a relation from a to b called the graph of f. We do not distinguish between a function f from a to b and its graph. The relation graph of the function f has the property that each a in a belongs to a unique ordered pair ab in the relation. On the other hand, any relation f from a to b that has this property gives rise to a function f from a to b where f of a is equal to b for each ordered pair ab in f. Consequently, one may equivalently define a function as follows. Definition. A function f from a to b is a relation from a to b such that each a belongs to a is the first component of a unique ordered pair ab in f. Example 6. Consider the following relations on the set A consisting of 1, 2 and 3. F is the set consisting of ordered pair 1, 3, ordered pair 2, 3 and ordered pair 3, 1. G is the set consisting of ordered pair 1, 2 and ordered pair 3, 1. H is the set consisting of ordered pair 1, 3, ordered pair 2, 1, ordered pair 1, 2 and ordered pair 3, 1. F is a function from a into a since each member of a appears as the first coordinate in exactly one ordered pair in f. Here f of 1 is equal to 3, f of 2 is equal to 3 and f of 3 is equal to 1. G is not a function from a into a since 2 belongs to a is not the first coordinate of any ordered pair in G. H is not a function from a into a since 1 belongs to a appears as the first coordinate of two distinct ordered pairs 1, 3 and 1, 2 in H. Definition. Two functions f from a to b and g from a to b are said to be equal if f of a is equal to g of a for every a belongs to a. That is if f and g have the same graph. If f is equal to g, we write f is equal to g. Pictorial representation of functions. Although we do not distinguish between a function and its graph, we will still use the terminology graph of f when referring to f as a set of ordered pairs. Moreover, since the graph of f is a relation, we can draw its pictures such as arrow diagram and plotting the points in a plane, as was done for relations in general, and this pictorial representation itself is sometimes called the graph of f. Example 7. The arrow diagram in figure 1 defines a function f from a, the set consisting of a, b, c and d, into b, the set consisting of r, s, t and u in the obvious way. That is, f of a is s, f of b is u, f of c is r and f of d is s. The image of f is the set consisting of r, s and u. Note that t does not belong to the image of f because t is not the image of any element of a under f. Example 8. Let a be the set consisting of 1, 2, 3, 4 and 5 and let f from a to a be defined by the diagram in figure 2. Find the graph of f as a set of ordered pairs. Find the image of f. Find f of s where s is the set consisting of 1, 3 and 5. Find f inverse of t where t is the set consisting of 2 and 3. Solution. The graph of f consists of all ordered pairs a f of a where a belongs to a. Hence f is the set consisting of ordered pair 1, 3, ordered pair 2, 5, ordered pair 3, 5, ordered pair 4, 2 and ordered pair 5, 3. The image of f is f of a and it consists of all image points. Since only 2, 3 and 5 appear as image points, we have f of a is the set consisting of 2, 3 and 5. F of the set S is f of the set consisting of 1, 3 and 5 which is equal to the set consisting of f of 1, f of 3 and f of 5 which is equal to the set consisting of 3, 5 and 3 which is equal to the set consisting of 3 and 5. The element 4 has image 2 and the elements 1 and 5 have image 3. Hence, f inverse of t is f inverse of the set consisting of 2 and 3 which is equal to the set consisting of 1, 4 and 5. Plotting the graph of a polynomial. A real polynomial function is a function f from a subset of r to r of the form f of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 plus etc. plus a1x plus a naught, where the a are real numbers. Since the set of real numbers is an infinite set, it would be difficult to plot each point of the graph. However, the graph of such a function can be approximated by first plotting some of its points and then drawing a smooth curve through these points. The points are usually obtained from a table where various values are assigned to x and the corresponding values of f of x are computed. Example 9. Figure 3 illustrates the above technique using the function f of x is equal to x square minus 2x minus 3. Vertical line test. The defining condition of a function f from a to b, that a belongs to a is the first component of a unique order where a b in f, is equivalent to the geometrical condition that each vertical line intersects the plotted graph at exactly one point. Hence, a set of points in the plane R2 is a function if and only if every vertical line contains exactly one point of the set. Example 10. Determine which of the graphs in figure 4 are functions from R into R. Solution. The graph in figure 4a is a function since every vertical line meets the curve at exactly one point. The graph in figure 4b is not a function since any vertical line to the right of x is equal to 1 meets the curve at more than one point. The graph in figure 4c is not a function since any vertical line to the right of x is equal to 2 does not meet the curve at any point. However, the graph in figure 4c does define a function from D into R, where D is the closed interval minus 2, 2. Composition of functions. Consider the functions f from a to b and g from b to c, where the codomain b of f is the domain of g. This relationship can be pictured by the following diagram. Let a belongs to a, then its image f of a under f is in b, which is the domain of g. Accordingly, we can find the image of f of a under the function g, that is, we can find g of f of a. Thus, we have a rule which assigns to each element a in a an element g of f of a in c, or in other words, f and g give rise to a well defined function from a to c. The new function is called the composition of f and g and is denoted by g composition f. That is, if f from a to b and g from b to c, then we define a new function g composition f from a to c by g composition f of a is equal to g of f of a for every a in a. The functions f, g and g composition f can be diagrammatically represented as follows. Attention, we emphasize that the composition of f and g is written g composition f and not f composition g. That is, the composition of functions is read from right to left and not from left to right. Example 11. Let f from a to b and g from b to c be the functions defined by figure 5. We compute g composition f from a to c by its definition. G composition f of a is equal to g of f of a is equal to g of I is equal to t. Similarly, it can be seen that g composition f of b is r and g composition f of c is t. The above can also be obtained by following the arrows from a to c in the diagram of the functions f and g. Example 12. Consider any function f from a to b. Then one can easily show that f composition 1 suffix a is f and 1 suffix b composition f is f, where 1 suffix a and 1 suffix b are the identity functions on a and b respectively. In other words, the composition of any function with the appropriate identity function is the function itself. Associative property of composition of functions. Consider the functions f from a to b, g from b to c and h from c to d. Then, as pictured in figure 6a, we can form the composition g composition f from a to c and then the composition h composition g composition f from a to d. Similarly, as pictured in figure 6b, we can form the composition h composition g from b to d and then the composition h composition g composition f from a to d. Both h composition g composition f and h composition g composition f are functions with the domain a and target set d. The next theorem on functions states that these two functions are equal. Theorem 1. Let f from a to b, g from b to c and h from c to d. Then h composition g composition f is h composition g composition f. The proof of the theorem is left to the assignments. Remark. In view of theorem 1, we can write h composition g composition f from a to d without any parenthesis. One-to-one, on-to and invertible functions. Definition. A function f from a to b is said to be one-to-one, written 1 1 if f of a is equal to f of a prime implies a is equal to a prime. That is, f from a to b is 1 1 if different elements in the domain a have distinct images. Definition. A function f from a to b is said to be an onto function if for every b belongs to b there exists a belongs to a such that f of a is equal to b. That is, f from a to b is onto if every element of b is the image of some elements in a, or in other words, if the image of f is the entire target set b. In such a case, we say that f is a function of a onto b, or that f maps a onto b. Remarks: the term injective is used for a one-to-one function, surjective for an onto function, and bijective for a function which is one-to-one and onto. If f from a to b is both one-to-one and onto, then f is called a one-to-one correspondence between a and b. This terminology comes from the fact that each element of a will correspond to a unique element of b and vice versa. Example 13. Let a be a non-empty set. The identity function 1 suffix a is a one-to-one and onto function and hence is bijective. Example 14. Consider the functions f from a to b and g from b to c. Prove the following. If g composition f is 1 1, then f is 1 1. If g composition f is onto, then g is onto. Solution. If f is not 1 1, then there exist distinct elements x and y belongs to a for which f of x is equal to f of y. Thus, g composition f of x is equal to g of f of x is equal to g of f of y is equal to g composition f of y. Hence, g composition f is not 1 to 1. Therefore, if g composition f is 1 1, then f must be 1 1. If a belongs to a, then g composition f of a is g of f of a belongs to g of b. Hence, g composition f of a subset of g of b. Suppose g is not onto, then g of b is properly contained in C, and so g composition f of a is properly contained in C. Thus, g composition f is not onto, then g must be onto. Definition: a function f from a to b is called a constant function if f assigns each a belongs to a fixed element in b. Definition: a function f from a to b is said to be invertible if its inverse relation f inverse is a function from b to a. Equivalently, f from a to b is invertible if there exists a function f inverse from b to a called the inverse of f such that f inverse composition f is 1 suffix a and f composition f inverse is 1 suffix b. Attention! Suppose f is a function from a to b and if b dash is a subset of b, then we can discuss the inverse image f inverse of b dash even if f inverse is not a function. Theorem 2. A function f from a to b is invertible if and only if f is both 1 1 and onto. Proof: suppose f is invertible, then there exists a function f inverse from b to a for which f inverse composition f is 1 suffix a and f composition f inverse is 1 suffix b. Since 1 suffix a is 1 1, f inverse composition f is 1 1 and hence by example 14 f is 1 1, and since 1 suffix b is onto, f composition f inverse onto, and hence by example 14 f is onto. That is, f is both 1 1 and onto. Now suppose f is both 1 1 and onto, then each b belongs to b is the image of a unique element in a, say b cap. Thus, if f of a is equal to b, then a is equal to b cap, hence f of b cap is equal to b. Now let g denote the mapping from b to a defined by g of b is equal to b cap. We have g composition f of a is equal to g of f of a is equal to g of b, which is equal to b cap is equal to a, which is equal to 1 suffix a of a. Hence, g composition f is 1 suffix a. F composition g of b is equal to f of g of b, which is equal to f of b cap is equal to b, which is equal to 1 suffix b of b. Hence, f composition g is 1 suffix b. Hence, by the definition, f is invertible and its inverse is the mapping g. Geometrical characterization of 1 1 and onto functions. We now discuss the geometrical meaning of the concepts of being 1 1 and onto of a real valued function f from R to R. We first note that f may be identified with its graph and the graph may be plotted in the Cartesian plane R2. The function f from R to R is 1 1 means that there are no two distinct ordered pairs a1b and a2b in the graph of f. Hence, each horizontal line in R2 can intersect the graph of f in at most one point. The function f from R to R is onto means that for every b belongs to R, there is at least one point a belongs to R such that ordered pair ab belongs to the graph of f. Hence, each horizontal line in R2 must intersect the graph of f at least once. Hence, the function f from R to R is 1 1 and onto, that is f is invertible if and only if each horizontal line in R2 will intersect the graph of f in exactly one point. We illustrate the above properties in the next example. Example 15. Consider the following four functions from R into R whose graphs appear in figure 7. f1 of x is x square, f2 of x is 2 raised to x, f3 of x is x cube minus 2x square minus 5x plus 6, and f4 of x is x cube. Observe that there are horizontal lines which intersect the graph of f1 twice, and there are horizontal lines which do not intersect the graph of f1 at all. Hence, f1 is neither 1 1 nor onto. Similarly, f2 is 1 1 but not onto, and f3 is onto but not 1 1, but f4 is both 1 1 and onto. The inverse of f4 is the cube root function given by f4 inverse of x is equal to cube root of x. Remark, sometimes we restrict the domain and codomain of a function f in order to obtain an inverse function f inverse. For example, suppose we restrict the domain and codomain of the function f1 of x is equal to x square to be the set D of non-negative real numbers. Then f1 is 1 1 and onto, and its inverse is the square root function given by f1 inverse of x is equal to square root of x. Similarly, suppose we restrict the codomain of the exponential function f2 of x is equal to 2 raised to x to be the set R plus of positive real numbers. Then f2 is 1 1 and onto, and its inverse is the logarithmic function to the base 2 given by f2 inverse of x is equal to log x to the base 2. For a non-empty set S, we denote the set of all 1 1 and onto mappings of S onto itself by A of S. We state some properties of A of S in the following theorem. The proof is left to the assignments. Theorem 3. If sigma, tau and mu are elements of A of S, then 1. Sigma composition tau is in A of S. 2. Sigma composition tau composition mu is equal to sigma composition tau composition mu. 3. The identity function I from S to S is an element in A of S, and sigma composition I is equal to I composition sigma is equal to sigma. 4. There exists an element sigma inverse in A of S such that sigma composition sigma inverse is equal to sigma inverse composition sigma is equal to I. Theorem 4. If S has more than 2 elements, we can find 2 elements sigma and tau in A of S such that sigma composition tau not equal to tau composition sigma. Proof. Let x1, x2 and x3 be 3 distinct elements of S. Define the mapping sigma from S to S by sigma of x1 is equal to x2, sigma of x2 is equal to x3, sigma of x3 is equal to x1, and sigma of S is S for any S belongs to S different from x1, x2 and x3. Define the mapping tau from S to S by tau of x2 is equal to x3, tau of x3 is equal to x2, and tau of S is equal to S for any S belongs to S different from x2 and x3. Clearly, both sigma and tau are in A of S. Now, sigma composition tau of x1 is equal to sigma of tau of x1 is equal to sigma of x1 is equal to x2, and tau composition sigma of x1 is equal to tau of sigma of x1 is equal to sigma of x2 is equal to x3, and hence sigma composition tau not equal to tau composition sigma. Let us summarize what we have discussed here. In this session, we have discussed the concept of a function between two sets. We have seen that function is a special type of relation. We have discussed various ways of representing functions. We have observed the associativity of composition of functions. The concepts of one-to-one, onto and invertible functions are also discussed. Before closing the session, try the following assignments. Let A be the set of students in a school. Determine which of the following assignments defines a function on A. To each student assign his age. To each student assign his teacher. To each student assign his sex. To each student assign his spouse. Define each of the following functions from R into R by a formula. To each real number, let f assign its square plus 3. To each number, let g assign its cube plus twice the number. To each number greater than or equal to 3, let h assign the square of the number, and to each number less than 3, let h assign the number minus 2. Let f is a function from R to R be defined by f of x is equal to x square minus 3x if x greater than or equal to 2, and x plus 2 if x less than 2. Find f of 5, f of 0 and f of minus 2. Let the function f from R to R be defined as follows. F of x is equal to 3x minus 1 if x greater than 3, x square minus 2 if minus 2 less than or equal to x less than 3, 2x plus 3 if x less than minus 2. Find f of 2, f of 4, f of minus 1 and f of minus 3. Here are some books for your reference. Ian Herstein, Topics in Algebra, Whaley Eastern Limited, New Delhi, 1975. Nathan Jacobson, Basic Algebra, Volume 1, Hindustan Publishing Corporation, India, Delhi, 1993. John B. Fraley, A First Course in Abstract Algebra, 5th edition, Addison Wesley, California, 1999. Vijay K. Khanna, S.K. Bhamri, A Course in Abstract Algebra. Vikas Publishing House Private Limited, New Delhi, 1996. Thank you for watching this program. See you in the next session. Until then, goodbye.